Hello, and welcome to my filling out of an exam number 4A for the test that you're going to be taking tomorrow. Hopefully, some of you will find this of use. This time around, instead of an unwieldy camera balanced up on some old books that I had, I've got my tablet system and I'm just recording the screen. So hopefully, this will be a little bit easier to work with, but a little less dynamic at the same time. So let's go ahead and dive in. So we start with the discovery. Oh, don't forget my name. So we start with the discovery of the structure of DNA was published by Watson and Crick, but we need the name of the exceptional scientist who performed the X-ray diffraction studies, and it's important for scientists to get their due, especially when it comes to people like Watson and Crick who didn't feel like it was necessary to actually credit people, and so we always need to remember that it was Rosalind Franklin whose X-ray diffraction studies really were what was allowed people to know about the double helix structure. And that's just something you're going to need to remember. And so now we have question number 2. What are the 3 forms of kinetic energy that molecules possess? And of course, you can think about it if you have just like some sort of real simplistic molecule like this. There's a variety of motions. All kinetic energy is just motion. So you can just sort of imagine how many different ways can we imagine this thing moving to represent its kinetic energy. So obviously you could have the molecule just moving around, and just moving around in a position is called translation. You could imagine the molecule rotating, spinning round and round. That's stored energy right there, just like there's stored energy in a bicycle tire or a gyro. So, and that's just simply rotation. And also, bonds are not actually like real stiff bars. They're more like springs. There is a back and forth motion where bonds will be at different lengths, and so we have we refer to that as vibration, as the bonds themselves sort of bounce into smaller and larger distances. And so those are the 3 forms of kinetic energy that you're going to have. And again, visualization is good, but whatever, it's mostly going to be a memorization of those 3 different forms of energy. Then we need to name 3 factors that affect the rate of a chemical reaction. And I've got a formatting problem here where all 3 of them have been moved like this for me translating from a PDF to a Word file. But again, we just need to think about the kinetics that you've gone over and the different aspects of it. There's more than 3 possible factors. I'll give you 4 good ones. So the most obvious one, and let me scroll a little bit. The most obvious one is going to be the temperature. Because of activation energy, and you've seen if you heat a reaction vessel up, then the reaction is going to go faster. That's several of our labs this semester. You would heat things up to make sure that the reaction proceeded quickly. Again, also as important would be the concentration of the reactants. If there's more concentration inside of a vessel, then they're much more likely to have the reactants reach and touch each other, so the reaction will proceed more quickly. Also, the physical state of the reaction is important. Reactions are going to proceed much more quickly in a liquid than a solid, and proceed much more quickly in a a gas than as a liquid, because they're able to move around more freely, so there's many more chances for the right reaction and to take place. And also you can consider the fact that a catalyst can affect the rate of a reaction by creating a different pathway, which is much quicker and more favorable to use. So then we have our next question: how does the magnitude of the activation energy affect the rate of a chemical reaction? And you're going to be asked to do something like this earlier, but I'm just going to draw the vague energy system here. We'll assume something that's exothermic. So we've got an initial energy state and a final energy state. It would like to be down there, but there's always this awkward transition moment. And so that's your activation energy. And so all of your molecules are bouncing around, trying to hit each other with the enough energy that they can roll up this hill all the way to go down to the bottom. And so obviously, the higher the activation energy, like if I had another diagram and it was just the tiniest little bump and then you could go down, it's much easier to beat that hill. So the higher the activation energy, and I'm just going to put EA so we can move on. The higher the energy of activation, the higher the activation energy, the slower the reaction will be. And so oftentimes what a catalyst is able to do is dramatically lower the activation energy by having a new pathway. And that's how they're always being good. And now we're talking about catalysts again here with number 5. Adding the correct catalyst to a vessel will increase the rate of the reaction. And we need to explain how adding a catalyst increases the rate of an endothermic reaction with respect to the pathway of the reaction and the activation energy. And I'll just draw another little idea. So it's endothermic, so we're actually going to a higher energy level. But even for an endothermic reaction, there's always going to be a more awkward state where bonds are not quite where they want to be, and so there's a higher energy level. But catalysts are great because the catalysts are able to lower the activation energy. And they do this by allowing a new pathway. So it's important to remember that catalysts will never change the energy level of the reactants or the energy level of the products, just that activation energy system. And then for number 6, according to the kinetic molecular theory, increasing the concentration of the reactants will typically result in a reaction proceeding more rapidly because, and again, this is just when you get down to the molecular level, it's, you can imagine like a box of gas particles, and they're all have random trajectories and they bounce against the walls. So if there's only 4 particles in there, that's a lower concentration. There's only so many opportunities for them to collide with each other. And of course, each of them have different energy levels. So one of them is proceeding a little bit faster than the others. But if we had a box with, dozens and dozens and dozens of particles bounding around with different energies and trajectories, it all comes down to thinking of it as sort of like billiard balls bouncing into each other for the most part. The collisions are more frequent. And there's more sufficient energy. And those are good for for the billiard ball systems, but that analogy breaks down sometimes because actually two molecules actually need to hit each other with the correct orientation. When you're doing that esterification reaction from the lab or from your last test, you actually need the molecules to impact each other in the correct orientation. If the functional groups that are reacting with each other don't actually get close enough to react, then nothing's going to happen with that collision. So it's got to be the disadvantage of this tablet method. And so those are the three, what's going on in the small scale with the various molecules bouncing into each other. They've got to collide, have enough energy that they can break and reform bonds in that sort of awkward transition state, and that they actually need to be oriented in the right way so that the bonds that are breaking and reforming are close to each other for that to take place. So now we have number 7. Is the combustion of propane in oxygen an exothermic or an endothermic reaction? So we've got some good hints here as to what we're working with. First, it's propane, and if you ever watch your King of the Hill with propane and propane accessories, you know that that's a hydrocarbon that is burned. We can even draw it out if we wanted to. I think we're going to have to in a second. And it's a combustion reaction, so things are burning. So you would expect from that a lot of energy is being released. And so if energy is being released, then that has to be an exothermic reaction. So now for B, we've got to write the balanced chemical equation. So we got to think back all the way to the previous exam. What does propane tell us? So prop would tell us that there's 3 carbons. And then the ane means nothing else special is going on, so it's just H's everywhere. But for a balanced reaction, we don't need the structure, so we can just do a more simple C3, 3, 4, 5, 6, 7, 8, C3H8. And we know a combustion reaction is just the combination with oxygen. And both of these are going to be in the gas phase. And all these combustion reactions, just like our own body, just produce carbon dioxide and water. Now the trick is to balance it, and deciding which molecule to start with is always the important thing. And for combustion reactions, especially, starting with the carbon is great. The oxygen is not a good place to start with because you've got this O2, which, you can mess with that in any way you see the need to. So I always like to start with the carbon. So we see over here on the reactants, we have 3 carbons. So we've got to have 3 carbons on our product side, and the only source of carbon on the product side is carbon dioxide. So we need to have 3 carbons to balance that. Then we look at the propane. We've got 8 hydrogens in the propane, so we need 8 hydrogens over here. And there's H2O, so we need 4 water molecules to get 8 hydrogens on the product side to match with the 8 hydrogens on the reactant side. Now we can think about the oxygen. How many oxygens have we created now? So there's 4 oxygens here from these 4 water molecules, and there is 6 oxygens here from the 3 CO2s. So we have 10 total oxygen, which means we need 5 O2 molecules to balance it out here. So there's your balanced chemical equation. 1 propane, 5 oxygen, 3 CO2, 4 H2O. And it's always good to start from the most restrictive things. So like the carbon and the oxygen and the reactants are linked together. So you'd start with one of those, and then oxygen is the last thing you can mess with because it's much more flexible. And that's all you had to do there is write the balanced equation. So we'll move on. Okay, so on the following image, draw an energy diagram showing the relative energies of the reactants, products, and transition state for the combustion of propane and oxygen. So we remember from the first part of this question that it is an exothermic reaction, which means that we need an energy state for the reactants and an energy state for the products that is lower than the reactants. And so we're going to have a transition, but there's always that awkward phase of transition that is higher than either the reactants or the products. And then eventually we flow down here. So now we've got the relative energies, but you got to remember here. So this section right here is your activation energy. Whatever, we're not using units here, but whatever energy level from the reactant's energy level to the top of the transition state, that is your activation energy. And so that's going to be one of the main factors affecting the speed of the reaction. This is why propane will not just spontaneously combust when it's combined with oxygen. You need to provide it a little bit of heat to get the reaction going. And then the reaction speeds up from that point because it's releasing so much extra energy that the temperature maintains itself. So now we go in here explaining what characterizes a spontaneous reaction. And we're flipping over a little bit now, because previously what we were looking with those energy diagrams and the activation energies, we're talking about kinetics. Propane combustion is a spontaneous reaction. It's always spontaneous, but the activation energy means that it doesn't always just immediately happen. We just need to provide a little bit of energy to get going. But other reactions are just not spontaneous at all. You would have to physically force them to take place. And this goes into the deeper thermodynamics. So a spontaneous reaction is something that it might need activation energy, but it's that you don't have to specifically provide energy for it. So it's a reaction that occurs spontaneously. No, you can't just restate the question. It occurs continuously without outside assistance or continuously provided energy. And so, just as a brief aside, there's some things that are technically spontaneous that you wouldn't think about. A diamond is just carbon in a different kind of configuration. And that configuration only happens under the intense heat and pressures of, the Earth's crust. So that's not a spontaneous reaction. You need that intense pressure and heat pushed into the diamond to make it take place. And once a diamond is dug up, it is technically a spontaneous reaction for that diamond to turn back into graphite carbon, but the activation energy and the kinetics for that to happen are so extreme that it effectively never actually takes place. You could theoretically say, put a diamond in a room and then come back 10 billion years later, and maybe by then it would have turned back into graphite. But in our lifetimes, diamonds will always remain diamonds because the kinetics just aren't there. So now we need to look at the three factors that determine if a reaction will occur spontaneously. And I don't know how much Dr. Thies has gone into the concept of Gibbs free energy, but I'm just going to list that equation here just in case, because that's really great for determining this. So Gibbs free energy is a way to determine whether or not a reaction is spontaneous with specific numbers that go into it. And you've got the enthalpy, which is represented by H for that, which represents sort of heat. And then you have the change in temperature and entropy, which is represented by an S. And so these three things represent what will determine whether or not a reaction will occur spontaneously: the enthalpy, the entropy, and the temperature. And you can see how these things can work against each other or can both lead to something being spontaneous. And so if we bring this forward, we can say which physical state has the greatest entropy. And so again, entropy is about how many possible configurations could something be in. So if you've got a solid, it's relatively boring. It's just going to stay in that small configuration of being a solid. If you've got a liquid, then all of those molecules can flow around and move, unlike the solid where it's just tightly vibrating in one place. And then the gas, it can be anywhere, bouncing around endlessly. And so there's more potential states for the gas. The gas is what has the highest entropy. And explain our reasoning. I guess I just did that. Is that the gas has the most freedom. There's more. So yeah, the gas has the more freedom to move around. It creates more disorder, and more disorder is leads to higher entropy. And then again, poor formatting here, but it says the process of a solid changing into a liquid. Oh, that's we see that every single day. Melting. Nothing fancy or special. Just solid to a liquid is a melting process. Does this physical process require energy, or does this process produce energy? And there's a couple ways you could tackle this. I always like to think of the ice cream example. In old school ice cream machines, they would use ice with salt. And the reason they would do that is just like for the reason that we put salt on the roads. When you add salt to the ice in the ice cream machine, it forces it changes the melting point of the ice, so it makes it melt. And the melting ice actually requires energy, and it gets that energy from the cream in the ice cream maker. So that allows you to reduce the temperature of the cream to make ice cream very, very quickly as compared to if it was just regular ice. And so I always think of it like that. But just any time that you're changing your physical state to a higher entropy level, it requires energy. And the way you can think about that, just as again a tangent, is if you look at the Gibbs free energy. So if I increase the entropy, that leads to something being more spontaneous. So it makes sense that the reason that everything doesn't just turn into vapor is because turning to this higher entropy state of a solid to a liquid or a liquid to a gas also requires energy. So we've got that interplay, that you require energy, and that counteracts the entropy, so that only at a specific temperature does the entropy win out. And so you require energy to melt. And so under what conditions does this physical process occur spontaneously? It's going to be at the temperature above the melting point, the chemical. The chemical's melting point. So then we go into the next question, more with the So which of the following is an endothermic process? And we can just go through each of these. Well, the evaporation of water. Well, we just covered the idea that going from a liquid to a gas would be endothermic because it increases entropy really greatly. So that's probably what it is. But let's just look at the other ones real quickly. Burning of wood produces a lot of heat, so it's obviously exothermic. Explosion of a dynamite is a whole bunch of energy released. And the discharging of a battery is energy in the form of electrical current. So those are all exothermic reactions. They are releasing energy out into the world. And so it definitely needs to be the evaporation of water. So I think you could probably explain your reasoning by ruling out the other ones, but it'd be better just to talk about that, is that evaporation requires energy. To take place, so it is endothermic. And then now we've moved past that, and now we're talking about plastics. And the formatting is a little iffy here again, but given the choice, would you use a thermosetting plastic or a thermoplastic for manufacturing a kitchen countertop? And explain our reasoning. So we got to remember what those mean. And really the name tells us so. A thermosetting plastic is, once it's set, it's not going to change much anymore. It's going to be very firm. And then a thermoplastic is one that reversibly can become flowy when you heat it back up again. So thinking about that, you probably wouldn't want kitchen countertops that could melt if you accidentally put a hot pot or something on them. So we definitely would want the thermosetting plastic. We'd want the thermosetting, and I'm going to screen this down. We want a thermosetting plastic because it keeps its shape. Under higher temperatures. While a thermoplastic will deform. Which is non-ideal for a kitchen. I guess there's some values assumed within the idea of what you'd want in your kitchen, but we're going with that, is that we don't want things to start, we don't want our countertop to melt. So now we have explained the reason why low density polyethylene is less dense than high density polyethylene, and a simple diagram for the explanations. And so the difference between these is, based on various processes, how the polymerization reaction takes place. So first, let's draw a diagram of low density polyethylene. So polyethylene is just real simple carbon bonds. We're not going to bother with the hydrogens and all of that. But so you would expect some large chain like this, but low density polyethylene will have lots of side chains connected to it as well. And so like this, you can see that you can't really line it up well. And so let's just, so low density polyethylene contains side chains. And so if you think about, and then you had like another polyethylene right here with other side chains, you get these sort of dead spaces because they can't really line up as well with each other. And then high-density polyethylene is really carefully designed so that there are no side chains. It's just an infinite system like this. And then if you thought about, you can have another polyethylene carbon just right next to it. So it can be really nice and dense. High density polyethylene has no branching, allowing very close. And very close equals dense configuration, I guess, yeah. Or in more simple English, they fit closer together. And that's just all it is the low density is all side chained out, so it can't really click together like tight little Legos like the high density polyethylene can. So then we have, for the following structures, what kind of polymer is represented, addition or condensation? And then we need to identify the bond functionality, whether or not we're looking at an amide or an ester. So just for each of these, I think the best way to do it is to just look, is there an obvious functional group? And if so, then it has to be a condensation. If there's not an obvious functional group in these, then probably what it meant was that there was some double bond that existed and was removed in order to allow for an addition polymerization reaction. So we just need to remember these two things. An amide always is going to be a nitrogen attached to a carbon with a double O. This is sort of the critical thing that we're looking for an amide. And then the ester, if you recall, is going to be this structure inside the middle of it. So, the more stuff is going on here and more stuff is going on here. And the same thing for the amide. So let's look at our very first guy right here. And what I notice popping out at me right here is we've got a nitrogen and then a carbon with a double oxygen. So I'm going to circle that because that is a condensation with an amide bond. And that's just, once we see one of those telltale structures, we can tell that was an amide condensation polymerization. So now let's go to this next one. And we're looking through, and there it is again, a telltale piece. A carbon double oxygen and then an O in the middle. So that's also condensation. And it is an ester bond. And then now we look at this one. All we've got is carbons and fluorines. There's no ester group. There's no amide group. So this has to be addition. And addition reactions don't have a functional group to circle. So it's just addition, and that's it. And so there you go. Just always look for these two basic structures. And if you can't find that basic structure, then it's got to be an addition polymerization. And now we're sort of doing the reverse. Draw the reaction and the resulting repeating unit to form the polymers from the following monomers. And so here we see there's no carboxylic acid, there's no amine group, nothing that would allow us to form esters or amides. So it has to be an addition reaction. And we also see, look, we've got a double bond, which is what you need for that reaction. And so to show the process, I'm just going to draw another of this same molecule here. Oh, sorry, that's a Cl. And so this double bond breaks and links to this carbon over here, and presumably then this double bond also breaks and links over to another one. And then that leads to, so the double bond is gone now. We used the double bond to create this link. And so we've got one carbon here, We'll just do all 4 of the carbons to show this reaction. It's fine to show it. And so our first carbon here has a chlorine on it, and then a hydrogen. This next one only has hydrogens. Then this next carbon, again, has a chlorine on it, and a hydrogen, and a hydrogen, and a hydrogen. And remember, this is a polymer, so we don't actually add an extra hydrogen to the end. We just do this system and put a little N that it can, eventually these reactions do terminate, but theoretically they could just proceed on forever bonding like this. And we don't know without more special information that you're not going to need to worry about in this class about how long the chains are. So we just put an N on there. And even just the parentheses is probably fine. So then again, let's take a look at our next one. This time we don't have a carbon double bond, but what we do see are the telltale signs of a reaction. We've got a carboxylic acid group and an amine group, which are the classic things to turn into an amide. So I'm once again going to just draw this exact same molecule. And R is just, something else is going on over there. And so the same general process is the OH and this H will break off, and this N connects here. And so again, we're just going to draw the whole structure out. N, there's only going to be one H on the end here, so then we have a carbon, then R, and an H, double oxygen, N, and make sure we have another in there. So you can see, so that, and then we've got that telltale amide group here. And that's what we're looking for. So that bond together like this. And then we look at this one. Oh, look at that. So you might think something fancy is going on with the benzene, but no, again, we don't see any nitrogen. We don't see a carboxylic acid group. So that double bond's got to be what's happening. So again, I'm just going to draw a copy of this molecule with a really quick, crummy benzene ring here. And again, so this double bond, okay. So again, so this double bond breaks and leads into these. And so the double bonds are all gone. But there's this first carbon, just had oxygen on it. The second carbon has the benzene ring attached to it. And then the same thing here. We've got the first one, which just has carbons. And a benzene ring. Like so. So yeah, it's important to remember that the benzene ring is only going to be alternating on it because of the way that this molecule is put together. And what we have here is what is known as polystyrene, which is what we make styrofoam out of. So very exciting, isn't that? Learning all these real world things. And so just again for these is when you see the functional groups, then it's going to be a condensation. If you don't see those functional groups and you're going to see a double bond between carbons somewhere, it's an addition. And you just need to remember that to keep in mind where the things are going. So then we ask, how are proteins held together and how do they maintain their distinctive shape? Well, you got to remember that proteins are made up of amino acids, and the amino acids have some side chain group, and then on one side they've got an acid, a carboxylic acid group, And on the other side, they have an amino group, and that's why they're called amino acids. And if you look at that, oh, those are the telltale signs of an amide bond. So this N will connect on, and we'll get these bonds like this. And so, again, a little too sensitive on the system. And so we'll have a side chain here. Sorry, then, and then so another nitrogen would bond onto that, and then we'd have some other side chain, etc., etc., etc. And these side chains could be anything, because there's quite a few amino acids that you don't need to worry about, but just that you can see that proteins are held together with amide bonds. They are sometimes referred to as peptides when we're specifically talking about amino acid bonding, and they hold shape with their side chains. You know, these R's can be a variety of different things, which all have unique physical structures and electrical and different properties, which allow for all these unique shapes and configurations to take place. So then we need to name 3 polymers that are encountered in the human body. So we've just talked about one, right? Proteins are a polymer in the human body, but you know, we can think of a lot of other ones potentially. I think you definitely argue that DNA is a polymer that's inside of the human body. Those are nucleic acids that are bonding together. Let's say that we've got cellulose, which is, you know, different sugars that we bond together inside of our body. There's also, instead of just DNA, there's RNA, which is also the structure of a protein. You know, we're really held together by polymers inside of our systems. You could even argue, I guess, starch potentially. We don't produce starch ourselves, but again, it's just it's something that is in plant material. It's a biological polymer. So we'd probably go with that as well. But just any of these things that are long chains that of smaller pieces held together, protein, cellulose, DNA, RNA, is what we're going to be looking for that one. And then we have, what are 2 relatively unique physical properties of water? And really, water has a huge number of unique physical properties, and because of its unique structure. It's got the hydrogen bonding. It's got this, open bond here, which gives us so it leads to a very high melting point, a high boiling point. Most interestingly is that the solid is less dense than the liquid, which is why ice floats. Again, also because of that, it has a very high specific heat. You could even say, you know, it's got a high surface tension. Just everything that has to do with its particularly strong hydrogen bonding, and so that it has very strong intermolecular forces to it that make it have all these much higher values than what you would think for the size of the molecule. And just any 2 unique physical properties will be fine. I'm sure you can imagine a couple of more, but I always find that the fact that the solid is less dense than the liquid and that it has a very high relative melting and boiling point are the most interesting and specific ones for water. And what do these properties have on Earth? And you know, you can go into a whole bunch of these as examples. You could, for instance, note that ice floats, allowing for inhabitable water bodies in winter. Oceans, because of the high heat capacity, regulate the temperature well. We maintain the liquid water at a temperature similar sized molecules would be gas. So just any sort of justification that, whatever it is that was unique about water in sort of what property that you've answered, it's, if it wasn't that way, if it didn't have an unusually high melting point, etc., then Earth wouldn't be able to support the life that it does, more or less. That's a very loose question, and is the last question. Now we're down to the 4B, and so hopefully going through this is a little bit helpful. As always, I encourage you to look through the exams yourself. To see how you're feeling about the knowledge. You can look through the 4B one after you've looked at this comparatively, and hopefully this will be of use to you. I apologize for how late this is coming out, but certain issues have prevented me from doing it earlier. But good luck, and I will see you next time.